the best paper for cognitive robotics at IROS, and he had all possible prestigious fellowships until now.
Okay.
Enjoy.
Okay, thanks for having me here, and thanks for the introduction, Costas, and thanks everyone for coming. So I'm Jiajun from MIT, and I'm going to present our work. As you can see, we call it physical scene understanding. So we humans live in the physical world, right? So we effortlessly see and reason about the physical world and interact with it. So of course, we want to build machines that have the same capacity, right? We want machines to also be able to see, interact, navigate in the world, and interact with the things, and maybe talk to humans. But to do that, let's first review what our human capacities are. What are the things that we can do in this physical world? So I'm going to show a few videos. So this is a video where we have balls and a few simple objects that interact with each other. And you see the balls are rolling, and there are collisions happening. And this is a video on the street in London where you can see there are cars and humans and in front of a very complex background, right? All those buildings and trees, but you can see the humans and cars walking. And this is a video where the baby trying to play with this shape sorter. She probably has this kind of shape and try to put it in. And this is a video where the baby is trying to go to his or her mom after hearing the call. So what can we see in these videos? Right, these are all daily scenarios. We are probably familiar with all these. Maybe not the first one, but you can easily recognize all the objects there as well. So what can we see in these videos? So let me group them into three major categories. So the first one is perception, right? Going from bottom up, you're able to see recognition, right? Perform recognition, see the balls and the blocks. And you can also, see in the cars on the street, you can do a 3D reconstruction. Imagine what the 3D shape of the object would look like from a 2D image. And you have the ability to imagine, right? Can you think about the ball now, but in a different color, right? If can I imagine a car, but in a different shape? As well as the ability to imagine and put it back to scenes, right? So just like, in scene manipulation, how would a car look like in a different pose? So these are about perception. But going beyond that, there is physics, right? By seeing objects interacting with each other, you can sort of infer, okay, what will be the relative mass of these objects? This object is probably heavier than the other. You can't really get accurate prediction, but you can get a rough estimation. And you can predict what's going to happen, right? So after the ball collides, what's going to happen in the future? And then you can use it to plan how I should really interact with the ball to achieve a certain goal. And you can extend your ability to even non-rigid objects or like fluids. Like I have coffee in my cup. I don't want to spill it over. Right, because I can predict, I don't want to do this because I can predict it's going to pour onto my keyboard. And going even beyond that, you have the ability to perform abstract reasoning. So this includes, I see this very short video where you have a few objects interacting, and then you can connect that to language and to answer questions like, how many objects are there? Or what will happen in the future? Or what if I get rid of an object? As well as going to an even deeper question that is concept discovery. How do I know what cube means at first place? Why cube refers to object shapes, not object color? And how these concepts are composed to represent more complex objects like shapes, like chairs. So these are all the things we humans can do. Then how are they organized, right? How are these concepts connected? So here is a model for it. So this is an image I took from the block tower dataset from Facebook AI. And for a simple image like this, we can assume there is an underlying physical world state behind it, which consists of object intrinsics, that's object geometry, appearance, and materials, mass and frictions, and object extrinsics, like the positions and velocities, as well as the scene descriptions, the lightings, camera parameters, and the process of going from these world states to the underlying image, to the actual observation is, what people in computer graphics study, right? So that's computer graphics. You can do it for many frames. Across frames, there is physics going on, right? You take the current states and perform an action on it. Here, the action could be gravity. And the physics tell you what's going to happen, right? How states transit. You can do it for many frames. And many problems we care about is actually trying to invert this process, right? To infer the states from the observations. That's what we call inverse graphics or physics, inverse physics. And another way to say, or to to call inverse graphics is people say, oh, computer vision or perception. I mean, it's a way of seeing what computer vision is. Not the only way, but one way. And above that, across all these states, there's something that is shared. That's, what are concepts? Right? Objects is always there. The physical properties is always there. The shape is always there. And also the structures and regularities. There are 4 blocks in a row. They're probably of the identical shape and stuff like that. So these are connected to all these states via usually techniques like program synthesis and program execution. So this is how we are able to connect the 3 major areas of our ability. That's perception, physics, and reasoning, and they are connecting this way. And then if we go back to the things we can do to see how they fit into this picture, then there are basically 2 major categories. One is, they're trying to go bottom up to invert the states, right? Trying to do recognition or reconstruction like doing inverse graphics, and seeing physics, seeing object properties like trying to do inverse physics. And the other direction is you can go top down, right? How you can move along these arrows, using 4 physical predictions for control and planning, or going down to use techniques from computer graphics to generate 3D shapes, generate 2D images, to imagine how the object will look like in a different pose. So these are really the things we want to do. And if we look back into what current machine C understanding system they're mostly doing, they're doing very well on problems like recognition or generating pretty pictures like human faces or transferring the styles across pictures, thanks to the development of deep networks and large data sets. But if you map them back to the things we can do, you realize they're focusing on 2 particular problems. One is recognizing object categories, semantics, and the other is just generating pictures. But they can do very well on this, but we really want the whole landscape, right? So how can we really build machines to not only do these 2 things, but do everything that we humans can do? And that's what my research is really about. And so if we want to learn to achieve all these tasks, then now there's a fundamental question of what really needs to be learned, right? So along this learning spectrum, on one end, there is this what we call full learning or pure learning approach. That is, you just try to learn everything, right? So just like you can learn to classify an image if it contains a cat or a dog, you can also learn to classify, what will be the material, what will be the texture of the object, what will be the action that I should take given the current state. That's like learning policies, as well as learning to predict future, whether the tower is stable or not, learning to directly predict the stability labels. So with these learning methods, especially with deep networks, after they are trained, then in inference, they're very fast, right? You can get very efficient inference. But as we know, they really require a lot of data, and for different tasks, you really need to have different data sets for them. So it's a little hard to also generalize across tasks. It's good to generalize within the data distribution, but if you want to train a model from a particular task A to transfer to a task B, it's usually pretty hard. And as we have seen, we have all those domain knowledge we have developed, right? That's in computer graphics or physics. So these are all the things we already know about the physical world. So why don't we just take all these models, and then you can have a pure modeling approach that requires no learning. I just optimize, search for the best states that really explains my observations. And that doesn't require that much data to train, probably no data even at all. And it can, because the model really captures the various scenarios in the physical world, it's pretty good in generalization. But it really is very slow, right? Whatever method you use for searching or like MCMC sampling, they're just very slow. So here we're thinking about this hybrid approach, which will combine learning with modeling. And just using the knowledge we already know about the physical world, graphics and physics, and to guide us in building learning systems. So they really tell us, what we can learn, and also what will be the training targets, what will be the intermediate repetitions, and what kind of data we need to have for these learnings. And in particular, as we just said, we're dividing our usage of learning into 2 major categories. One is learning to invert this generative process, to infer the physical world states from observations. And the other is we can use learning. Sometimes, the knowledge we have, physics, graphics, they're just not enough. We can learn to augment it, to build better physical simulators, to build better graphics engines. And hopefully, this can achieve the best of both worlds, where you can inference very fast, and you can require little data to train, and you can generalize better. So here's a general principle that is for everything we learn, we definitely want to learn it for a reason. Right? We don't want to learn everything from scratch. We want to learn according to the knowledge and structure of the physical world. So here's a demo of what we can do here if we develop such kind of approach. So given a single image, the image on the left is the input, we're able to reconstruct the scene. So that's kind of the reproduction of our systems. And then we were able to combine them with physical simulators for forward simulation and graphics engines for rendering. Then you can generate what will you believe to be the future. And you can compare them with the ground truth future. So I'm going to play the videos to show our prediction and ground truth side by side. But our method only take the first image as input. Right, so you can see it really, first it's not identical to the ground truth, right? They really the blocks, they're not in the exact position. But it really captures all the intuitions you have, right? Whether the block tower is stable, how many blocks are falling, and to which direction they are falling. Right? And beyond that, because you're really recovering the states and reconstructing them, you can use that to generalize and answer questions like, if I have this input image, I reconstruct it, then what if there is a force coming from the right, or what if I'm poking a block on the top? Then what's going to happen with that? As well as if I already see a block tower and it's going to fall, then what will be the stabilizing forces that I can take, what actions I should take to prevent it from falling? Right. All right, so this is really what we want to do, right? To combine learning with modeling, to learning to invert, and to learning to augment to achieve a much larger landscape of sea understanding abilities just as we humans have. And then I'm going to present three. I want to really show you all these, but due to time constraint, I really want to focus on three of them. So it's reconstruction, scene physics, and dynamics modeling for planning. So this really covers the major work that is how we are learning to invert graphics engines, how we are learning to invert physics engines, as well as how we are learning not only to invert them, but also to augment them to build better physics engines. All right, so let's start with perception. So focus on the problem of 3D reconstruction. So why 3D reconstruction? Because it's a very important problem in our daily life, right? We have to understand object geometry to navigate in 3D, in the 3D world. I have to understand the shape of the cup to pick it up and to drink the coffee, right? And also, it's a very important problem in cognitive neuroscience, where a lot of research has been studying visual perception, whether there is a 3D representation at all, or if there is, then what kind of form it is. So the question here is, if I want to do 3D reconstruction, then what are the proper inductive biases that I should build into these deep networks for reconstruction? So as we said, we know a lot about 3D already, right? In particular, we know about computer graphics. So let's look at the forward process, right? If we want to, so the problem is to reconstruct the 3D shape on the right, like the 3D geometry from the 2D image. Then in computer graphics, there is, look at how it works. And this is a process of, image formation. So given the 3D shape, you put it in the environment, and there is a light source. And light source can send rays onto the object, and then it gets reflected into the camera. In front of the camera, there's usually a camera plane, image plane, that really captures what you can see of the object in the image. So it's really important to realize here that what is really in the image is the visible surface of the objects. Right? So you're seeing the full chair, you can see, okay, that there's a chair in the image, but you are really seeing is the visible surface of the object. You're not really seeing anything behind it, although you can use your prior knowledge to imagine how the shape would look like. So definitely you can try to design a model that inverts this process by dividing it into two stages as well. The first is, I use depth estimation as an intermediate representation, going from a color image, RGB input, to the depth map. So here the depth map is really a different representation of parameterization of the visible surface. And then the second step, really go from the depth map to the full 3D shape. Right. So here, the first step is what we call depth estimation. It's in 2D, and the second step is going from 2D to 3D. That's shape completion. So this is really using the knowledge we have from computer graphics to think about how it works and try to motivate our design of a vision system that try to reconstruct shapes from images. And this is our design. This is really the design behind our system, which we call VARNet. David Marr, we named it in honor of David Marr, who is a very famous computer vision scientist and computational neuroscientist in the 1970s and 80s, early 80s. And he proposed a theory that humans seeing 3D shapes via a number of intermediate representations, and one of them, a very important one, is called 2.5D sketches, which is really something about the surface. So you're seeing 3D shapes via surfaces, and the 2.5D sketches has different representations for surfaces. Here we're using some of them. That's depth map, as we just said, and the surface normal maps. That's about orientations of the surface, where the pixel is pointing at, as well as the silhouette. So we have now this bar that has two modules, as we just said. First one is 2.5D sketch estimation, estimating the visible surfaces. And the second is going from the visible surfaces to the full 3D shape. So here, the 2.5D sketches, oh, I'm a little behind. Okay, and again, going from the 2.5D sketches to 3D shapes. And here, another important observation is why 2.5D sketch is important. Because, an image, that's kind of an image of the sofa, and it has a lot of information, right? It has all those, object textures and lightings, the interaction between them, so it makes it look realistic. But if you're really caring about the 3D geometry of the object in the image, then all those texture lighting information, they don't really matter. What really matters, or what image really tells you, think about what the image really tells you about the geometry. Everything you can get about the geometry from the image is actually the surfaces, right? So the 2.5D sketches. So in that sense, the 2.5D sketches, you can also see it as the sufficient statistics of that the image gives you about the 3D shapes. So in that sense, you're also, if you're looking at the diagram, like going from inversion, going from observation towards states, you're dividing into two stages. The first is going from 2D images to 2.5D sketches, and the second is going from 2.5D sketches to 3D shapes. So here are some results of this system, which you can see it works pretty well even in the presence of very complex backgrounds, and sometimes it can also recover, the geometry of the objects even when the chair is not in a kind of uncommon shape. And sometimes, it can also recover the very complicated structure, fine-grained structure of the objects. And usually, 3D ground truths are very hard to get. So given the image, it's really hard for me to understand, to get annotated data on what the ground truth shape is like. But luckily, for things like IKEA chairs, you can actually have the ground truth. So here you can show you can see the reconstructions and compare them with the ground truth. And it's not perfect. They have all those, discontinuity that you don't really want to see in the reconstruction. But it really captures, the rough structure of the object just from a single image in the presence of colored backgrounds. All right, so this is about 3D reconstruction, but an important aspect of human seeing 3D shape is our ability to generalize to novel objects that we've never seen before, right? So in front of me, there are all those things, and some of them I've seen, but this thing, I don't know what it is, I probably have never seen it. But I can imagine what the shape will look like, even if I cannot really see the back of this, I don't know, some kind of thing. So we really have this ability to imagine using our prior knowledge, such as objects are often symmetric, objects often have smooth surfaces, to complete the 3D shapes, even for an image of an object I've never seen before. How can we model do that? Right? If we directly test the models, which here we train it on chairs, planes, and cars, they're the three major common categories of object shapes, and then we test it on the table. And this is what we are using, what we're going to get. This is a model which we took as a baseline, but some Marnet results are pretty similar. So does it look like a table? Not really. It looks more like an airplane, because if a model is trying to directly predict, for any image that you give as input, then what they're going to essentially do is trying to find out the nearest neighbor in the training set and saying, okay, chairs, planes, and cars, which one looks most like tables? Well, this object I've never seen before, but airplane at least have a flat surface, so I probably just give you an airplane. So how can we really generalize our model, build a better model to do that? So let's look again at the second stage, the depth to 3D shape, the shape completion stage. So again, the depth map is what we call it part of a 2.5D sketches, but it's really realized in 2D, right? So it's a 2D image of depth map. So when you're going from depth map to 3D shapes, the 3D completion network is actually over-parameterized. It's learning a deterministic mapping. What is it? It's learning the depth from visible surface, the 2D to 3D projective mapping. Right? So projecting depth into 3D is actually a deterministic and fully differential process, right? That's something people have been studying for decades about how the camera works, and they write all those projective equations. So if we already know about these things, computer graphics tells us about these things, why we have to relearn it? So why don't we just build it in particular because it's differentiable. So we developed this system, which we call generalizable reconstruction, or genre, in which instead of directly predicting 3D shapes from 2D images, or 2.5D, the depth maps, we first project the depth into a partial surface, and then complete the surface. So the network doesn't have to really learn to do 2D to 3D projection. we only focus on pattern recognition, how we can really go from a partial surface using knowledge like reflection symmetry, as well as repetitions and smooth surfaces, these priors to complete the shapes. So now if we test it on the same image table again, and this is what you're going to get, right? It really captures all the observations you have. I mean, it's still not perfect. It has a little bit of non-smoothness, but it really captures the observations you have. It has 3 legs, it has a flat surface on the top and stuff like that. And you can generalize to other NC classes. Right here we compare with a baseline called AlexNet, which is trying to generate, like, given a single image, it generates 100 different surfaces and try to compose them into get a 3D shape. Essentially, it's also kind of a direct prediction method. And compare with our generalizable reconstruction methods, you can see our method give you much more reasonable results, really captures the observations you have. And here, generating results on beds, sofas, and benches. In particular, you can see you can also capture some very small details, just like the legs and stuff, even just from a single image. And you can do some crazier generalization. What about generalization to non-rigid classes? Here you train on chairs, planes, and cars as before, but now we tested on human bodies. So here we just focus on testing depth to 3D, so we're just using depth map as input. And compared with the ground truth, now you get something that's also pretty reasonable, right? It really captures, the human bodies usually, has a lot of smooth surfaces and aligns with ground truth pretty well, even if the model has just seen cars, planes, and chairs. All right, so this is about reconstruction, but there are also other projects of doing reconstruction that I don't have time to talk about, including how we can using models to learn a prior of what shapes look like to really get the reconstruction much more realistic. As well as in many cases, you don't want a dense reconstruction. What about just reconstructing a skeleton of the object, really captures important information like key points and connections. As well as deploying into practical applications, what about reconstructing the 3D floor plan from a 2D image? And how can we learn to estimate 2.5D sketches themselves to do better 2.5D sketch, or people call intrinsic image decomposition? And as we said, the 2D and 3D data sets is very hard to get. So we are also trying to build data sets with pixel level aligned 2D images and the corresponding 3D shapes and poses. As well as once we have this reconstruction, what's the best way to really visualize them to make them look beautiful? Right, so this is about reconstruction. We are learning, but with the guidance of a graphics engine, to learn to invert it, to give us reconstructions that are, more realistic and generalizable to novel classes. And our perception really beyond graphics, right? We can see objects interact, we can infer their relative mass, as we just said. So can we now think about how to now put physics engine into the loop? So we're learning not only to invert a graphics engine, but also to invert a physics engine to get you the physical object properties. So this is a system we developed a few years ago, which we call the Galileo, because it really replicates the experiment from Galileo's ramp experiment. So it's like this. You have an object on the ramp, and then you let it slide down, and it collides with another object on the table. And it's pretty simple, right? But because the physical object properties are different, some objects don't really move, some objects really moves and hit the object, and sometimes, because some objects are much heavier, after the collision, the object can actually travel a long distance. So we humans can infer, okay, after the collision, based on behavior, what would be the relative mass or how heavy the object is? We don't have an accurate estimation, but we have a rough estimation. So can we build a model to do that? So now think about everything we talk about graphics, and now replace the graphics with a physics engine. Just like in graphics, you need 3D shape to get a 2D image. In a physics engine, you will first need a physical object model, right? A model of object mass and friction and position and stuff, and then you send it to the physics engine. And the physics engine will give you what will be the velocity vectors, how the object will move in that particular scene. And then you can combine them with a recognition algorithm. Here we just use a pretty classic tracking algorithm to get how the object actually moves, right? What will be the actual observations you have? And then you can compare these two, then you get a likelihood function, which really tells you, okay, how good your physical property estimations are. If your estimation of mass and friction are really accurate, then you should be able to generate the simulation to be very close to the actual observation. And then this could be used as a signal to guide your MCMC sampling. This is like the full modeling approach, where it really requires minimal learning here. And here's a demo of how it works. So given the object sliding on the ramp, then here is in the simulation. At first, you can see the friction is too large, and then the friction could be too small. And after a few iterations, it converges to the state which really aligns with the observation pretty well. But as we said at the beginning, these pure modeling approaches, they're usually very slow. Just here, in this very simple C and MC sampling, it could take 30 seconds to a minute to get a good answer. So can we accelerate this process, right? Can we actually use learning to invert physics and to do a better job here? So now, just like we use learning, you now take an image to predict geometry. Here, we're not really predicting a 3D shape, but we're trying to predict what will be the mass of the object in the image. And then, for the MCMC sampling, instead of starting from uniform prior, we're now starting it from the estimations from the neural network. And with this, augmented approach, we can actually realize, the sampling actually converges to a much better state. It also converges much faster. And an important benefit of having these kind of models in the loop, or physics engines in the loop, is now we're able to generalize. So here is a quick demo. I'll just give you one data point for training, which is something like this. You see the object slides down, and then, okay, slides down and hit the object, and there is collision happening. And now I'm doing a testing. Now I have a larger object, and I let it slide down, but only show you the moment to the collision, before the collision happens, and ask you the question of, okay, where the green box will be after the collision, is it A, B, or C? But how many people will say A? How many people will say B? How many people will say C? Right, so about 95%, 98% of people say, okay, it should be C. And you're right? As expected, if I really play you the whole video, there's a C, right? So once you have these, generative models or simulation engines in the loop, you're able to really generalize and to answer these questions. And so does our model, right? So in all these kind of future prediction tasks, we compare its performance with humans as well as some baselines. And then we realize, it has actually a pretty good accuracy compared to human performance. Also has a pretty good correlation with human responses. So here are some qualitative results where, for different cases, here the orange cross is the model prediction, the white cross is the ground truth, and the heat maps are the human predictions. So it actually aligns with human predictions pretty well in most cases.
How well can we generalize to the slope of the ramp?
Right. What if the ramp, the slope of the ramp? Yeah, that's interesting. So we actually tested it, and so surprisingly, it was a little bit surprising originally to me. Is if I vary the ramp angle of the ramp, then and I tested, whether we asked them the question is if I vary the ramp, the angle of the ramp to make it, less inclined or more inclined, then will the object still be stable, or is it going to fall, or at which how fast it's going to slide down? And surprisingly, the model performance is not very good. It's only slightly above chance. And then we tested on humans and realized, humans also have a slightly above chance performance on this. So there's an interesting coincidence here. But so we want to really dig deeper into it to see if that explains anything.
In this application, if you wanted to be able to handle different surfaces, same angle, but let's say Teflon versus sandpaper, is it clear how to augment your modeling, or is that not clear?
Right. So here, in this experiment, we're assuming the surface is all the same. But just like, varied angle of the ramp is like varied angle is like, it's object is more likely to slide down, and if we change the surface, it's like changing the friction, right? So the object can be more or less likely to slide down. So
you're guessing that a simple Coulomb friction model could be added into your representation.
So it's more like, think about the modeling approach I said at the beginning. If you just use a physics engine, and you should be able to find out the right friction that really explains the observation. Now, even if it's on a new surface, and if with this kind of data augmented approach, if you're just training the model to predict frictions of the surface on one particular surface, then on the generalization, you're going to suffer a little bit because the prediction of the model is not going to be right. But hopefully, with the simulation engine loop, you can actually correct your estimations. After a few sampling, you realize, okay, my original estimation of friction is too small or too large. So I can actually, by having this recognition model and generator in the loop, you should be able to generalize to different surfaces once you have a new data point on that surface. Although initially, the learner may give you something that's not very accurate. All right. So this is about estimating physical object properties. A few other works that includes, we can combine our work on estimating physical object properties and estimating geometry to really decompose the object into different parts where each part has different physical object properties. This is more likely the case in real world because we know objects are not always homogeneous. And you can also use it for scene parsing, right? Once I have an image and I try to parse it into these cuboids that represent different objects. Sometimes the cuboids can be floating in the air, they can be penetrating into each other. So if you have a physics engineer to help you, you can get these stable reconstructions. It's a little hard to see. Variation is a little small here. And there are cases where the object movement is so small, it's really hard to see from the eyes, but you can tell from the vibration, right? You do spectral analysis, you can actually infer the sheet structure, how they connected from vibration. And there are not that many data sets for physics, right? So we've been collecting these, we call it physics 101 data sets because it's like an introductory data sets, but also because it has 101 objects in 5 different scenarios in more than 20,000 videos. And on the other hand, I mentioned we are interested in understanding cognitive and as well as neural basis about how these models correspond to human behaviors and how they explain neural responses in these physical stimuli. Right, so that's about inverting not only geometry, inverting a graphics engine, but also inverting the physics engine to get physical property estimation. Third, I want to show you how we use learning, not only inverting these simulation engines, but also augmenting them. So you've said, okay, modeling is so good, physics engine, graphics engine are so good. Then why do we just use it? Why do you want your learning to augment it? What's wrong with the off-shelf simulators? So I'm going to show you why such an augmentation approach is important and useful. So first, in object manipulation, we really want these high-fidelity dynamics models. So here's an example where the robot trying to push an object, and the surface can be non-smooth and stuff like that. And researchers in robotics have developed very nice analytical models for these kind of scenarios. They date back to 1992, where you have a pusher, you have an object, then there's contact location and pusher velocity, and from these parameters, you're able to actually compute object velocities and rotations using these very nice analytical models, assuming the sticking contact, so the pusher doesn't really move along the edge. So what's wrong with this model? Well, first, it's very good, but sometimes it's not enough. So let's look at the actual push, where we have this, this is the real motion, and this is what's predicted by the model. And at first, it's pretty good, but in the long term, and if we try to match them, I realize there's a deviation, right? So the real motion really deviates from the simulation. And because of what? Because the objects is not homogeneous. Sometimes one part could be more, could be denser than the other part, and because the surface is not smooth, there are all this roughness, microfrictions, and stuff like that. And second, if you try to push it multiple times, then this is what you're going to get, right? Every time the outcome is slightly different, and then you have this very complex distribution of possible outcomes. So dynamics is stochastic, also for all those reasons, all those variations in the object geometry and surface. So in these cases, learning can be helpful. So you have this idea of augmenting physical simulators, but with learning. So first, you have a physical simulator. As we said, it's null, so it doesn't require any learning. It's pretty good. But on the other hand, it makes some simplifying assumptions, and it's deterministic. Oops. And then you have this learning approach, which is, if you implement it as a neural network, which is more expressive. It can capture all those uncertainties and stochastic, but it really requires a lot of data to train. So what about we combine them? Right. So here, the state and actions are first sent into the physical simulator, and the physical simulator is going to tell you, okay, what's going to happen, its own prediction of future states. And then its prediction, as well as the current state and action, are sent into the learner. So the learner is trying to learn a residue, or learning to correct the physical estimator's prediction, and to give you what it believes will be the possible outcomes, and also to make a prediction of distributions. It's like it's stochastic predictions. So hopefully this kind of approach could be more expressive first, because it can really, and there is also, of course, you can add these recurrent approaches to make predictions not only for a single step, but for a long-term prediction. You can start from a current state and predict what's going to happen in the long term. So hopefully this approach can be more expressive, capture the multimodality and stochastic, and also requires less data to train to be much more data efficient than a pure end-to-end learning approach, because we already built in what we know about the physical equations. So the network doesn't have to learn that again, and then all the network has to learn is things about the object and things about the surface that really explains the things that analytical equations cannot explain. So these are the data-driven methods used for. So here's some results on this MIT push dataset. So that's the paper called More Than a Million Ways to be Pushed from Alberto Rodriguez group from MIT. And so where they have the robot push object many times, and every time they record the position and state and along over time. So we can actually see that the model has a more accurate prediction than a physical simulator. So here are two example pushes. One is push to the corner, the other push to the edge. This is the ground truth. And these are what the physics engine is going to give you, which is okay, good, but not perfect. This is what a neural network is going to give you, which is much better, but still not perfect. If you augment them, combine them together, then you get something that's much more accurate than either using a physics engine alone or using a neural network alone. And it could be more data efficient than data-driven approaches. Right? So here we're comparing our method with a neural network. So the x-axis is the training examples, and the y-axis is the error. So you realize if you want to achieve an error of like 1%, relative error of 1%, our model only requires around 700 training data. And a pure neural network approach requires about 2,000, a little bit more than 2,000. So it's like 1/3 of the data we need compared with the neural network. It can also generalize to new shapes and materials, right? Generalize better than the baselines. So here, when testing on new shapes or objects made of a new material, our hybrid approach performs better than a pure learning or a pure simulation approach. So yeah, the gray one are ours, and the yellow and blue ones are the others. And it can capture the uncertainties. So here we're comparing with another learning approach, which is based on Gaussian processes. And the red dots are our predictions, the yellow crosses are the ground truth, and you see they align pretty well. And our model can also capture the multimodality, right? You can see two modes here in the output. Well, the baseline is focusing on the major mode.
Tell me more about how do you create the physical simulator? Is it the simulator is differentiable, or is it like that's the rule?
Yeah, very good point. So first, the physical simulator alone you don't have to train it, right? It's these equations. And this hybrid approach, you combine them, and the physical simulator itself is differentiable. As you can see from those equations, they're just, yeah, it is differentiable. Yes?
When you use the learning systems to do function approximation of residuals rather than, do you find that the architecture is really important, or could you make use of Chebyshev polynomials or Taylor approximation?
That's a good point.
How important is the architecture once you start fitting residuals?
Yeah, that's a very good point. In this case, because data is actually pretty simple, so we find it's not very important. So we just use a pretty simple multi-layer perceptron, I think. Yeah, but I can imagine, in other cases, yes. I'll answer your question in 2 slides, if that's okay. So of course we can deploy the system on a real robot and use it for planning and control. So here's a demo of this system, but now we deploy it on a robot, and we want to solve this highly interactuated problem where the robot trying to push the first disk and use it to push the second disk so that the second disk achieve a target position. So here it works pretty well on this. It's hard. And now let's go back to the question of whether the architecture is important. So think about whether other cases where physical simulator is not enough. For example, what about in, particle dynamics, right? If we want to write equations for particles, it's hard. I mean, people have been writing a lot of approximations, but they're still not good enough. So now I want to solve the problem of I want to shake the box so that the particles in the box really achieve the final configuration on the left, so to match what I want on the left. So what's the right way to shake the box? And so by learning this system and deploying on this environment, you are able to really actually achieve that, and it actually aligns pretty well with the observation. So here we are making an important architectural change. That is, for particles, the number of particles there is unclear. For different scenarios, it could be more and less. So simply a kind of fixed dimensional multi-layer perception is not enough. So, but something important or important inductive bias we have or from particles is particles, if we look at every local neighborhood, they're interacting the same way, right? Just like liquid. This part of liquid and that part of water, they always interact the same way. So we got inspiration from there, and we used what we called, what people call the interaction networks or graph networks, where you model every particle as a node. And the graph network is actually learning from the interaction of these particles and trying to simulate, how the particle will move by looking at its local neighbors and see, based on how they move, and trying to predict, how this own particle will move. So here is a very important architecture change here to really make it work on the particle system, as well as a number of other things, but that's the most important. Yeah. And other times where physical simulators are not enough is when you combine them with perception, right? Where if everything's going from visual data, from images, then perception system is not perfect and the estimation could be wrong. So can we learn to combine them together and then to replicate, to build these kind of towers or bridges from a single image? Just by seeing a single image like this, we're able to first see these objects and reason how they're going to interact so that I know if I want to replicate it, I need to start from the bottom. As well as when there involves humans, right? If I'm standing on the stage, am I going to move my hand up or down, right? This is something that physical law cannot capture. It captures, I cannot really move my hand to the far right, but it cannot really capture my own intention. So that's what we call visual dynamics, how we are learning to approximate multimodalities in human behaviors using a data-driven approach. As well as going beyond that, to also discover the structures, not only approximate the future prediction, but discover arms are part of the upper tarsal is part of the full tarsal, as well as to model the multi-agent interactions. All right, so here we covered how we're learning to invert graphics, learning to invert physics, and learning to approximate, to augment physical simulators. So I'm going to give you a very quick overview of the other part of the system. That includes, sometimes you don't want to not only augment physics, but you also want to augment graphics. So why we want to do it? Because you have a lot of people have been building things like ShapeNet, which is very large shape repositories, like 5,000 chairs and stuff. But it's often not enough, right? In the real world, there were millions of chairs, and many of them we have not seen before. Can you actually hallucinate new chairs? So here we use a technique called generative adversarial networks, which are very popular techniques in deep learning that you can actually generate beautiful images. But we deploy on 3D shapes, and then we can actually generate 3D shapes. But more importantly, we want to put computer graphics back into graphics. Just like in graphics, we take a 3D shape, put in a pose, and render it. We can also take the 3D shape, and consider its viewpoint, and to do differential projection. Again, it comes back, and get you in happy sketches. And then you have a 2D generative adversarial network to apply textures on it, so that you can generate not only 3D shapes, but as well as their corresponding 2D images with realistic textures in the matched pose. And you can combine this generative model, augmented graphics engine, with the inverse graphics system to do, object manipulation in the scenes, right? How the car will look like if it moves closer, or what if I get rid of some of the cars. This is about learning to augment graphics. And another important part is about doing higher level reasoning. So what does that mean? So we build all those scene parsing systems. So given an image, we are able to perform scene parsing. And if I already know object has attributes like materials and shapes and colors, then we can combine them with, for example, a language parsing model and turn the language, if the language is in a particular good form, then we can parse it into these semantic sentences or semantic programs, which you can actually execute, perform program execution, which is fully symbolic on the scene repetition to get answers. So you can do question answering. But there is a more important aspect. It's how do we know, object has shape or material or color at first place? Just like in computer graphics, it tells us, okay, object, if I want to put it into graphics engine, I need to have its geometry, have its texture. And in the physics engine, it tells us, okay, if I want to put an object into a physics engine, it needs to have mass and friction. But how do we know the object needs to have material or color, things like this at the first place to really solve this, question answering problem? Right. So here we resort to language. We use guidance from language. So this is a very simple example where I'm showing you two images. they're mostly identical. The only thing different is the color of the object. Then I ask you questions like, okay, what's the color of the object? You say red. And is there any cube? You say yes. And but in the second image, I ask you the same question. The only thing differs is the answer of red and green. So now assuming I'm someone who don't know English, which I really don't know much about. So if you look at red and green, then I don't know what that means. But by comparing them and also looking at those images, then I can realize, okay, red and green, it probably means something about color. More importantly, I can associate them with actually the RGB pixels, right? Red is associated with something that has a high R value, and green I can associate it with something with a high G value. So because the objects really have the same material, same shape, same size, and the only thing they differ is in color. So of course, we can generalize this to more complex scenarios and to learn more complex concepts like relational concepts, what does it mean by on the right of, and even more compositional structure. So here we let all these models work together. And with the only supervision from questions, answers, and natural images, we have these scene parsing model, language parsing model, program execution model work together in the form of neural networks to automatically discover what these visual concepts are and what these words means and how we can do visual grounding to associate them to the visual concepts. So here are some examples, right? You can actually learn concepts like, oh, cylinder, right? You can find, okay, well, that means cylinder can have different colors, different materials, different sizes. And that means matte. Matte is about material. It's not about shape or color. And because these recognition things are performed by neural networks, you can actually solve it on real images as well, where you can discover concepts like wolves or red, and compositional concepts like what does it mean by the closest living thing or person on a skateboard. And going even beyond that, you realize, it's not about just composing them together, but about, shapes like tables like this. They have 4 legs, but these 4 legs are identical. And they lay out on this 2x2 grid, right? So they form this regular layout. So they often have regular program-like structure. So we take inspiration from program synthesis, design this domain-specific language for shapes, and then try to represent shapes as programs. What's the benefit of that? Is we can do better shape modeling. If I have an image, I use SmartNet, then give you a 3D reconstruction, which performs okay. It gives you reasonable results, but you still have all the smooth surfaces, non-smooth surfaces that you don't really want. Objects are not symmetric. But if you now rectify it, improve it with shape programs, you realize, okay, it really captures all the intuition you have, right? Objects are purely symmetric, it has 5 legs, they lay out on this, 72 angles within each legs. You can also do that for images. Then you can do visual analogy. Think about visual analogy as actually learning relations between pairs of images. So look at these 2 images and think about what would be the relation to transform A to B. You can extract the relation in the form of programs, and now combine them with deep networks for inverse graphics and for rendering. Then what you can do is you can extract the relation and transform them, apply them on a real image, and using things like generative adversarial networks to give you pretty realistic reconstructions of the images, but with the right relation transfer. All right, so this is really about the whole landscape, about learning to invert, learning to augment. So to summarize, in physical C understanding, the first way to parse the phrase is what we call a common way, it's physical C understanding. That means on the task level, you want to not only do shape reconstruction or image generation, but you also want to understand the physical object properties, learning forward models, dynamics models, and learning visual concepts. But a different way to parse it is we call physical scene understanding. So you really want to understand the scene by understanding the graphics, the physics, the structure behind it. So what we know in different cases, right? In shape reconstruction generation, we know there are graphics in it, and we also know there are physics in it, and we know there are symbolic program execution in it. And what we are actually learning is to invert it or augment it, or invert a physics engine or augment a physics engine, or to invert and augment program execution engines. And also we take inspiration from cognitive science, which is about object perception, about intuitive physics and causality, about motion perception if I want to do future prediction, especially in visual dynamics paper, and about the concept of symbols, regularities, and hierarchies. And I like to emphasize the key message again is for everything we learn it for a reason. What's next? let's look at this video again. This is the very first video I showed you. So something we didn't talk about is you're not only seeing the video, you're also hearing the video. So the collisions between these blocks, right? The rolling of the balls, they all generate particular sounds. And using that, you can actually infer a lot about physical object properties. So we can actually do generative modeling not only for visual data, but also for auditory data. We can not only use a graphics engine, but also use acoustics engines that people have been developing in computer graphics. Of course, you have physics going on across them, right? So you can do these generative models of audio-visual data. So we build a data set, which we call Sound 20K, where you have different objects in different scenarios, and you synthesize both videos as well as the sound when they interact with these scenes. And we did some study and showed, as expected, that from visual data, you are able to recover a lot about object geometry, but from auditory data, you actually recover much more about object materials, because that's what really decides what the object is made of. And it's also about, if I'm seeing an image, I use things like Marna to reconstruct the shape. It's okay, it's good, but it's not perfect, right? For the first object, there is a little bit error in the pose. And sometimes the second object, you can see it's a little bit too thick than it should be. But with humans, we not only see the object, we also touch it, right? We also grasp the object. So we use our tactile information to refine our estimation of the 3D geometry. And after just a few touches, we can see the object is getting into a much better position. And in the second row, the object is now much thicker. And after 25 touches, you're able to get a very precise estimation of object shapes. And you can use it for manipulation as well, right? This is our very recent paper collaborating again with Alberto Rodriguez group. And the first author, Nima Fazali, he is also going to visit UPenn, I think, in a few weeks. So he's awesome, and so we work together, and he really, managed to get his work. Is we can use vision and touch data to not only do better shape perception, but to manipulate objects. It's hard to tell whether the block is movable from just visual data, but by touching it, you can easily tell. So you can combine them to actually do better manipulation to play games like Jenga. So this is about on the perception level. You want to do multi-sensor fusion. On the physics level, you want to not only do passive observation, not only seeing objects, hearing it, touching it, but also really manipulating it, right? Think about an object, and now here you do dynamic manipulation. You want to slide it down from the ramp. You actively have two objects interact with each other. And during this active exploration, you're able to build a model that learn a representation that encodes very rich information about object physics, like mass, and after a few steps of explorations. And you can also use the learned representation for manipulation. So here the goal is similar is like you want to push an object into a target position. Then you can achieve a much lower error in manipulation. That's about active exploration. On the reasoning side is, from physical theory understanding, can we also reason about the social interactions between objects. This is a very short video from Hyder and Seymour in 1944. It's almost 80 years ago. And it's very short. I only selected a short clip of it. So let me play it again. And so you can see from a few seconds, like, what is the circle doing? Right? It's trying to avoid a chase from the triangle, right? But we don't even see them. They in no sense look like humans, but just from these interactions from the geometric periods, we're able to infer their goals and intentions. So here, to solve that kind of problem, we probably need inspiration from not only intuitive physics, but also intuitive psychology and theory of mind. So here we're going from apparent motion to apparent behaviors. So that's about social interaction. And of course, we want to also, when we take inspiration from cognitive science, we also want to find if our model can capture the cognitive and neural basis of these intelligence. So here, an example that we try to replicate all those famous studies in developmental psychology in the 1970s, where you have two balls, they move behind a occluder, and then this is your belief. And then when the ball doesn't come out, you get a little surprise. But then suddenly, when the occluder fully goes down, you realize the ball disappeared, and that's the time you get super surprised, right? Because you have the notion of object permanence. Infants, when they dated back to 4 months or 5 months old, they already have this kind of concept, right? And they got very surprised when the object disappeared. So can we build computational models to capture that? And also, to locate them, when you're doing physical predictions, can you actually locate them and correspond with neural responses in human brain? Eventually, you want to generalize to real world. So this is a beautiful picture I took from the Penn Museum, actually. So you see a crystal ball in front of this transparent glass box, and behind it there's a screen showing some beautiful pictures. And what is supporting the crystal ball is a fancy, with all those very thin structures supporting it. And the crystal ball is fully reflective, and the glass box is fully transparent. So you have all those complex interactions between lights and object materials and object shapes, right? So how can we really scale our model to solve complex systems like this? And this probably requires innovations in both representations, what would be the right objects, scenes, and language representations, and what kind of data we need, how much we should be able to learn from real data, and how much we can learn from internal simulations, as well as what would be the right learning mechanism, right? How much, again, going back to the learning versus modeling spectrum, how much should be learned, how much should be modeled? And this really completes the whole picture of future work. And by then, I'd like to thank all my collaborators, especially my advisors, who was really insightful, and also my wonderful collaborators and funding agencies, and thank you all for listening. And we're a little out of time, I'm sorry, but any questions?
Any questions?
What method, like for the learning the shape program, is symbolic and desperate? Like what method do you use to learn that?
Neural networks. So it's like symbolic programs. You can parameterize it into a number of program sentences, and now each sentence you have a few parameters, and then you use neural networks to predict them. And then now the question is, I don't have data, right? Because there is no annotation at all for shape programs. This is new representation. No one has annotated any shape programs. So if you remember, there's something I didn't have time to explain, is when I say we have symbolic program execution in this, we're using, what we are learning is learning to both invert it and to augment it. What that means is I have a neural network that learns to take a shape to recover the shape program, and then I have a separate neural network that learns to execute the learned shape programs to generate reconstruct the 3D shape. So I'm learning to reconstruct it. And by having two networks operate together, by putting the priors in the intermediate representation, I force the latent representation to be in this particular program sentences, it's able to do that.
Oh, you mean you have the execution engine to like sort of like a
It's another neural network.
augmented data for your the program learning neural network.
Right, it's like it's a program learning neural network, it's a program execution neural network.
So it's an autoencoder.
Right, but it's a special type of autoencoder with a particular design in it. Right, just like in graphics, it's like you can see, we had a paper called neural scene derendering, which is like kind of we call it a generalized autoencoder, where you go from image to encode it into a representation, but it's the input that a graphics engine can take. Now your decoder is a graphics engine. Here, it's like you have an encoder into programs, now an executor, or your decoder is a program executor. Yeah, but now that one is more like neural network-ish.
Other questions?
Yes?
Everything you've built so far for rigid objects, if you wanted to handle highly deformed objects like, I don't know, clay, would it be the same method you showed so far?
Right,
Or
so
is there something different?
not necessarily fully rigid, because I think I have this example here, where we try to manipulate liquid. So we actually have that paper. So if you go to that ICLEAR paper, it's actually showing there's actually a real experiment on having a real robot, I think a KUKA, manipulating clay. So here we're using our graph networks or interaction-based networks to represent liquid or to represent clays as a collection of particles, and to use these kind of object-based or particle-based networks to capture their interactions, and then use it for model predictive control. Then you can actually manipulate planning to, okay, I want to really, if I want to deform a clay into a target shape, what are the action steps I should take? So I think the short answer is yes, you should be able to do that, but that probably requires an architecture change in the networks.
Other questions?
Yes?
So sometimes we also have some illusion of hallucination. Does your research have anything to do with that part?
Right, so that would be, well, there are two different ways of doing that, right? One is, let me see, it's a little too many slides. One is when you say, it's about, hallucinating how the shape will look like, right? Can you actually imagine, shape in a different, a new chair, or, okay, that's an example. Can you imagine